All right.
And let me share again. Okay. Everybody can see my screen again?
Yes.
Thank God I was here when that happened, but I'm going to talk to,
Yes.
I'll talk to Jared tomorrow. Okay. Let's get back to where we were. So on line 75, we have our generic version of this function. Now, one of the things I want to do is just remove some of the new syntax. Because I want to kind of talk to why we need a new syntax and then kind of where we are now with this. Now, if you look on line 75 here, right, and you see this print function that I'm writing. If you notice here, I'm just using the identifier T for the type, right? And the real idea right now is to tell the compiler, look, I want this function to be able to work with a slice of some type T to be determined at compile time. And it would be great if we could just do this, right? But the problem is that with this syntax, right, the compiler is assuming right now that I'm going to, in some source code file, at some point before I hit the build button, I'm going to define a type named T. This syntax assumes that somebody will declare a type named T before I hit the compile button or the build button. And the reality is that this is exactly the opposite of what we want. We don't want to have to define this type as something new. We want to replace T to be something that we know about at the time that we hit the build button. And so this is where the new syntax comes in. The new syntax comes in because we've got to be able to tell the compiler that T is a generic type and not a type that you should be looking for somewhere. And right now in the current draft, and the syntax that seems to make more people happy than not, is to use a set of square brackets attached to the name of the function using the keyword type, and then listing out those types names, the identifiers for these generic types in this list. So these are brackets, these square brackets define a type list of generic types that are to be determined at compile time. All right, and again, it's because we have to have a way to tell the compiler that T is going to be what I'm going to call a generic type to be determined at compile time, not something that we're going to define somewhere in some source code file. Now, a couple things here before I move on. The current tooling supports the use of parentheses. Originally, that was the only option we had up to maybe a month ago. A lot of people were complaining that it looked too much like Lisp and it was harder to read. But when using the parentheses, the use of the keyword type became important for the tooling to be able to parse this out. Then about 3 weeks ago, maybe 3 or 4 weeks ago, they added support in the tooling for the square brackets. People have been a lot happier about that. Now, because of the square brackets, you also can eliminate the use of the keyword type. Now, honestly, right now, you're not going to see me do that. And I don't know, it's because I've been playing with this for 2 months. My brain needs to see the keyword type. Or I just feel like there's more clarity with it. So throughout this code and throughout the rest of this talk, you're going to see me use the keyword type. I do want to share with you that right now you don't necessarily need to put that in there. And before a release is finalized, they're going to have to make a decision on whether or not to keep that as a requirement. I don't have any opinions either way, but you're going to see me using the keyword type here. Okay. And so now what I'm doing is I'm telling the compiler, there's going to be a function called print. There's going to be a type named T. It's going to represent a generic type. And in this particular case, we're using it to define that this function accepts a slice of some type T to be determined at compile time. Okay, great. So we're seeing the first generic function that I'm writing. You're seeing the use of this new syntax with the square brackets. We now understand why we need a way of directing or telling the compiler that T is going to be this generic type, not a type to be defined by us. And here we are. And you're going to see me removing these square brackets and putting them back in as we talk, because I just think it's easier to see the function first and then lay them in second. But now what we're doing is we're saying that T is going to be a concrete type, and then we can write code using Go's syntax to work with that concrete type of some type T, right? And the code comes back to this level of readability and comprehension. Okay, great. So with all that being said, let's run a little bit of the tooling now. So on line 86, I'm constructing a slice of integers, right? With 1, 2, 3, I'm constructing a slice of strings, A, B, C. And the idea is that I can pass that slice to all of these functions the exact same way, and they should work. So if I come back over to the terminal here, switch over to O1, I can now use my version of Go, which has the Go tooling in it, which again is the transpiler. This hasn't been implemented in the compiler yet. We just have a transpiler. And all this is going to do is take our Go2, notice the extension, Go2 file, convert it or transpile it into a .go file that can actually be built and run. And we get to play with the syntax. So you're seeing the same output, kind of boring, but we're seeing at least it work. And the big win here, right? I mean, the big win that we're trying to get to here is we've got a function that is, again, more comprehensible and readable than our reflect version. I can come in here now. Let's add our floats here. Doesn't matter what they are. There we are. We'll call this floats. And I can use the two generic functions that I wrote, and that's going to print. I don't have a print floats. Assert doesn't have the right case, so we can't do that. But if I'm doing everything right, then there we are, right? I don't have to write any more code, and we're able to print these out. And again, we could do it with the reflect package, where you have kind of that level of complexity, or we can get back to a concrete kind of language syntax implementation. Now, another thing I want to share with you is the concept of inferring. Now, this is a list of types. One of the things I want to share is you can have as many generic types listed here as you want. But in the examples I'm going to be sharing with you, they're just going to be one. And you also have the ability, when it's necessary, to pass the type information in to the function call, so to bypass the compiler's need to infer the type. So if you notice here now on line 90, I'm passing in, again using the square brackets, information for T. I'm not asking the tooling here, the compiler, to figure out what T is. I'm telling the compiler what T is. I'm saying it's an int, a float, or a string. And if I run this, all this should also be cool. Now, obviously, we don't necessarily want to have to pass it in, because if I don't pass it in, then print looks like a function call, like any function call we're used to. So being able to infer type information is a critical part of the implementation here that the compiler has to figure out. Now, in this particular case, the compiler can infer that T is an int, say for the call on line 90, because we're using T as the first parameter. So the compiler can do a little work and go, okay, first parameter is a slice of int. We're supposed to take a slice of T. T is an int, right? I mean, I'm making it sound simple. There's work there, but the compiler does, and the tooling is implementing the ability to infer that type information when it can. Okay, Brian. So this is our first example of the generic syntax. And to just kind of reiterate a couple of things here, the idea is that we want T to represent some type to be determined at compile time. that T is not a type that we're going to declare. So we're going to use the square brackets and the keyword type, and then a list of those identifiers that will be what I'm calling the generic types for that particular function. Okay, great. Now, in any real world program that we write, we're going to need to be able to define data types. Data types are going to be a really big, important part of anything that we build. And generics are going to fall into that as well. So let's start by looking at some user-defined types right now that are based on an underlying type. All right. And let's go through the same progression because I think it really helps. So on line 16, I'm defining a type called vector int, which is based on this underlying type, which is a slice of integers. And then what I've done is I've added a method named last. Now, what last is doing is it's going to return the integer in this case, since this is a vector event. The last integer in the vector, in other words, the last one for me is going to be at the highest index position in this vector, all right? And if the vector is empty, okay, if the length of this vector is 0, then we'll return an error and we'll return the 0 value for an int. Now, if I wanted to do the same thing for a vector of strings, well, again, I mean, these lines of code are pretty identical to these lines of code. All we're doing is changing out the type information, which is requiring us to change out the variable names for readability. But you can see here that we're returning a string instead of an int. The 0 value for a string is the empty string as opposed to the integer 0, but everything else is the same. Now we go back to the same thought experiment. Is there a way to, in the current version of Go, have a vector that can work with both integers and strings? The answer is yes. We could define our vector type to be a slice of the empty interface. Now this would allow us to store integers and strings and floats, and you can see the implementation of last is really identical, right? It's is it empty? Then we return the 0 value for an interface, which is nil, and the error, or we're going to pull out that last value out. But once again, every time we're dealing with the empty interface, we're kind of changing our semantics, right? Because one of the nice things about these vectors here at the top is that we know what data is being stored. So the usability of, let's say, calling last, knowing what the type is, the usability is higher. When we start working with the empty interface here, the code may not seem to have gotten more complex, but the usability is absolutely going to get more complex. Because if we're mixing data in this vector and I ask for last, we don't really know if we're getting an int, a string, or float, or what we're getting, right? And so there's going to be some usability issues here that could create, let's say, some error-prone problems. But there it is. There's the use of the empty interface. Now, how can we do the same thing with the new syntax for generics? So I'm going to get rid of this again, and we're going to talk about it. So what am I trying to do again? I really want to define a vector whose underlying type is a slice of T to be determined at compile time. And as soon as my brain goes some type T to be determined at compile time, then I know that T is that generic type, and we can bring back those square brackets back in to let the compiler know what T is. Now, what that means is that that vector by itself doesn't mean anything. Vector's always going to have to require some type T in its notation. So when you look at the receiver in this case, I want you to notice that it's a vector of some type T, and then we return a value of that same type T. Now, there's a couple of other interesting things here in this function. If we start here on line 61, it's very much the same. Is the vector empty? If it's empty, return an error. But we do have some interesting problem here because we want to return the 0 value for T. Now, this gets a little complicated because we need a universal syntax to be able to construct values to their zero value state regardless of what t is. And right now in the language, there's only two ways to do that. We can use the keyword var, like you're seeing on line 60, declare a variable called 0 of type t, which is what I'm doing, and then returning 0 in that, for that t. The other option to be able to construct a value of any type to its zero value state is using the built-in function new. Now, new returns pointers back to that construction, so we'd have to do that. But this is the other syntax choice that we have today. Either we declare a variable using the keyword var, or we can use the built-in function new to construct. A lot of people, when they think about this, ask, well, why can't we just do this? And the reason you can't do this is because not all values of some type t can be constructed this way. What if t is an int? If t is an int, you can't do that. That syntax doesn't work. And that's why you're going to have these two choices where this can be an int here or this can be an int here. These are your options. Now, I hate when there are options because now everybody gets to make a choice on what they want to use. And one of the things I'm hoping is that before this ever gets released, that at least the Go team, if not the community, comes together and defines what will be the better practice for these kind of zero value returns. And right now, I'm leaning towards the zero variable. I just think for the readability, and I think more Go developers, especially newer developers to the language, will better understand this than the dereferencing of a built-in function called to new. Okay, so we see that as well. Now, let's kind of look at the usability of all of this as well. So on line 70, what am I doing? I'm just playing a label, but I'm constructing a vector int with two values, the number 10 and the -1, and then I'm calling last. Now, when I call last, I'm going to get back -1, right? But one of the things I want to share with you is that because we know this vector works with integers, you know, writing code like this on line 73 is no big deal. I can immediately say, okay, if the number's less than 0, let's do some extra printing here, right? Same thing with the string, right? I'm storing these strings in the vector during construction. I call last. And the UTF-8 package has a function called valid string. And I know that I could apply valid string to the values coming out of last because this is a vector of type string. And I've made a little hacky hack thing here just so valid string reports, you know, true, right? Or false in this case. Now, this is great. Now, when it comes to using our vector interface, look at what I'm doing. I'm interlacing three different types of data, int, strings, and floats. And now when I call last, at this point, I am clueless on what came out in terms of what type of data. And now I'm back to these type assertions. If it's important that if the last value is an int, I do this. If the last value is a string, I do this. You see what I'm saying? And so even though the implementation of the empty interface seemed to be on par with the other implementations, you can see how the usability is always a problem when we have to start performing these type assertions, or maybe have to start working with the reflect package. It just adds a little more complexity. So what's super nice about having generics here is that I have a vector type that can become a vector of type int or vector of type string. Now, I want you to see something here from a syntax perspective. If we're going to be constructing these to their zero value state, we have to explicitly pass the type information. There's nothing that the compiler can do to infer type here. And that's why when I showed it to you with the function calls, there are even times when you might have to do it with a function call because the parameter list isn't leveraging the generic type. The generic type's being used maybe as an implementation detail. And in this case, there's nothing that the compiler can hang its hat on. Now, when it comes to this construction, however, the compiler can infer type. The compiler, in a final version of this is all we would have to do. because there is information here that the compiler can pick up. You may be saying, Bill, why are we not doing that now? Remember something, and this is important. The Go tooling is a transpiler. It's not the final or real implementation. And though the draft will say that this syntax is valid, they haven't spent all their time making the tooling 100% complete. And honestly, I think that would be a waste of time to make the tooling 100% complete, because once we lock in on the syntax, I'd much rather them focus that time on building out the compiler, right? So just be aware of that. Sometimes you might run into something where you're like, this should work. Why is it not working? And a lot of times it's because, yeah, we haven't implemented that yet in the Go tooling. But if it's critically important, we will. If not, we rather wait until we can get to the actual implementation. So you're seeing me pass the type information explicitly here on these constructions, even though I wouldn't necessarily have to. But what's beautiful is those type assertions are gone, and I know what type of data I'm working with. And again, comprehension and readability shine. So if we go into O2 and run the tooling again, there we are. It's all working. Because of time, I'm not going to do it, but I could easily copy and paste this now, change that out to a float, right? Change this out to a float 64 and it would work. I'm going to assume at this point you see that, you understand that, just because time is against me. Now, these are types where we're talking about a user-defined type that has a base type or an underlying type. But most of the types that we do work with in our Go programs tend to be struct types. So I want to share that with you as well. And what's interesting about this example also is that it will also give me the opportunity to talk about our value and our pointer semantics a little bit and some of the things around that. Now, I thought that the best example here was to create a container type, because I think one of the nice problems that Go can solve with this first release of generics is not just the removal of the empty interface. I mean, it's going to be the removal of the empty interface and reflection, right? But these container types, which today would have to use the empty interface, I think also we gain back a level of usability from that. So I'm just implementing a bare minimum sort of double linked list here so we can see the syntax. Now, again, when we look on line 14, I'm going to remove that for a second. I'm defining a node, right? The node is what we chain together in our linked list to store the data. And the whole point here is that I don't want to use the empty interface here, because then again, we're doing our type assertions, right? And that's adding code complexity. The idea is to be able to define a node of data of some type T, like you see on 15. Could be the int, could be the float, could be a user, could be whatever. And so again, since we're talking about some type T, we're going to take those square brackets and apply it again to the type identifier. You saw me doing that before. You saw me apply it to the function identifier. Now I'm applying it back to the type identifier. Now that takes care of the data that we're going to store of some type T. But we do have a double linked list here. We need to point back to the previous node and to the next node. And so this has to be a pointer of type node. But as I told you, right, this doesn't make sense. It's not just a node. It's a node of some type T. It goes back to that kind of construction syntax, okay? And so whatever the T is here, we apply it to the data, and then we apply it to pointers of that same type T, int, string, whatever that is. Now my list type also, what I'm doing is kind of containing my first and last pointers. And again, that's going to be of some type T. So you see our node of some type T. And our linked list should be using pointer semantics, and that's what we're doing. Now, to be able to add some data to our linked list, all I did is add one method called add. Now, there's some interesting syntax here, because remember, our method sets are going to match our type T declarations here. And in this case, I used a pointer receiver, which in this case, I mean, it should be a pointer receiver. But again, it's a pointer of list of some type T. Again, anytime we're going to have these kind of generic types, we're going to have this syntax. And it returns a pointer of a node of some type T where we accept a value of type T in the add. Now, the only interesting thing here in the implementation, not this is just wiring it all up, is the construction call here of node. And notice that we're passing T into the construction call here. Remember before in main, we had to actually provide an explicit type, but this is an implementation. It's a method implementation. And so we want to make sure that for whatever data this is, we're going to construct a node of that same type to be able to store data of that same type. So you're seeing the construction syntax again with T kind of flowing through it. And you can imagine the rest of the API there. Now let's just add some values to our linked list. So on line 44, I'm going to define another struct type named user. That's the data that we're going to store in our linked list. And then if you get to line 53, again, we're doing zero value construction. There's no way to be able to identify the type you want to use. So we're going to explicitly pass it during construction. And I'm going to use value semantics. I'm going to say that the list is storing user values, which then applies back to the add method, where you see me storing user values on the add calls, and then these data fields will be of type user. And then just to show you a little bit here, this list has decided to use pointer semantics, and it's going to store pointers of type user, which then apply back to the add method. Now we're doing user construction to its address. And then as I print these out, we'll see addresses. So if I switch back over here, switch over to example 3 and run the tooling, not spectacular, but you see values of, and you see the ampersand, you see the address of. Now, one thing I want to share with you is you might one day write maybe some sort of container type, and you might say to yourself, you know what? I never want the user working with value semantics. So what I'm going to do is like hard code the pointer semantics on line 15 into T. I'm going to hard code the pointer semantics on line 25, right? And now what you're saying is I'm restricting this data structure to just pointer semantics alone. Now you can do that, but you are, I think, causing two usability problems. I'm going to get rid of that for a second. One, I'm telling the compiler that T is going to be a user. But since we hard-coded pointer semantics, this add now requires this, right? If I don't do this, let's look at the compiler message now. See, the compiler message is telling me, well, Bill, you need pointer semantics here, right? And so now what we're kind of seeing is, though I'm specifying user, it's not necessarily obvious now that we're using pointer semantics. It was kind of down here when we were working. But now if I bring this back, the compiler is going to complain because everything is now double in direction, isn't it? Because now I'm passing a pointer of type user, and that is being substituted here. That's being substituted here, which can also create a little bit of more confusion here, right? But you're locking somebody into the pointer semantics. You know, these are things that can happen. And so I think one of the things I just wanted to share with you here was that it's kind of nice when it's reasonable and practical to allow the developer to choose the semantic that they want to use. So I want to work with value semantics, I'll just say user. I want to work with pointer semantics, I'll say a pointer of type user. And then T can take on that semantic, and the user gets to choose where they want to work. But I'm sure that there are going to be implementations here or there that you may run into where you're like, I don't care if the user wants to work with value semantics. I'm not going to allow that. And I'm gonna kind of hard code that pointer semantic in certain places. Okay, cool. So I've shown you how to write a generic function. I've shown you how to write two different types, user-defined types, one with an underlying type, one with the keyword struct. Let's see, it's 8:03. I'm giving myself another 20 minutes here, which is at least like 2 more things here that I have to share with you if we're going to get a more complete picture of the spec. Now, let's get back to our generic functions. The other generic function that I wrote was a fairly basic function, right? It was just performing linear traversals and then leveraging the print function to print out those values regardless of their type. But the reality is that you're going to write a lot of functions that aren't necessarily going to be able to work with all different types of data. There's going to be constraints that are going to have to be applied to data in order for those functions to be able to work with that kind of data. And one of the constraints that we actually have today are behavioral constraints, right? I mean, that's what interfaces kind of do. They define a method set of behavior, which defines a constraint of behavior that that data needs to exhibit. And I want to kind of walk through some of that. So let's start here on line 13 and 22, where I'm defining 2 more user-defined types. They're struct types, user and customer. And then on line 18 and 27, I add a method named string, which returns a string. And essentially what these functions are doing is they are stringifying a user and or a customer. And I've hard-coded the stringification, right? And I've kind of made it look like JSON. There we are. But it's a way of stringifying, maybe for logging, maybe for other things, what these entities would look like. And then the idea is, well, what if I have a collection of users and a collection of customers, and I want to stringify them all in another collection? Well, here's 5 lines of code that do it, right? We can get the length of the user collection here, and I can make sure that we have the right capacity for that slice. We can perform our linear traversal like we've done. And then the big key here is on the call to append, we don't just pass user, right? We have to call the string method because it's the string method that has the intelligence for stringifying a user. It's the string method against customer that has the intelligence for stringifying a customer. But what's nice is that the append function can work with these strings. In fact, you know, when you think about this, and I find this interesting, you know, Go has a set of built-in functions: append, make, copy, new, delete, close, len, cap. If you think about it, these built-in functions are generic functions, are they not? Append can work with a slice of any type and a value of the same type and perform that operation. When you really step back, thanks to the reflect package and the built-in functions, I mean, Go has generics, but let's be fair. The mechanics that are used to write those generic built-in functions are not extended to us, right? They're only extended to the language designers directly. And I think this is why you can turn around and say Go has generics, but it's not 100% fair because we don't get to necessarily use those same mechanics. The generics are giving us those mechanics, right? But here we are with append. But the big thing here is that, that this behavior is defined. Now, let's go back through that same exercise. Could I write a stringify version that could handle different entity types? I'm not going to go through this code. You've seen it already. Empty interface, type assertion, case statements. And if I had another entity type, we're doing some more copying and pasting. But the compiler knows that if we're dealing with a user or a customer, there's string. Question, can we write a fully generic version of this function today using the reflect package? And honestly, we can. Here it is. Now, we're looking at 13 lines of code as opposed to 5. And trust me, I had to do a little bit more work digging into the reflect package API. And if you just stare at this, it looks like gobbledygook. But if you walk through it fairly quickly, reflect on the value, is it a slice? We're changing our semantics again because you can't guarantee an output. Construct the right length for that outgoing slice, increment an I, validate, is there a method named string? If there isn't, changing semantics, but if there is a method named string, we do get to call it. And so the reflect package is giving me the ability to call that string method if it exists. I do have to do checks again if it's a slice and if it doesn't have a string method. But if all of that's in place, guess what? I've got a generic version of this function, but it's 13 lines of very complicated code with a change in semantics where we could pass nil or have to pass an error back to handle that. Okay, so let's get to our generic version. And as always, I want you to focus on the fact that we're back to the same 5 lines of code, the same 5 kinds of code we all love, we all comprehend and read, because it's language syntax around using a concrete type. However, let's go back through our exercise here. Now, I want to work with a value of some slice t. Well, what do we know? Brackets t, there we are. But I have a problem. You see, there is behavior here that we must have a guarantee that t, or at least values of type t, exhibit. Now look, I can write a function, maybe named Bill, that accepts a value of type user, right? And I could write a function, I'm going to use Bill again, I mean, you can't really reuse the same name. But what do we know about user and customer? We know right now that they both implement a method named string. And in case you don't know, the fun package and the log package each define an interface called stringer. And stringer defines a single method set of behavior, which is a method named string that returns a string. And today, I could write both of these functions. Now, when you look at the function on line 111, what I want you to see here is this is a function that's asking for data based on what it is. It's a concrete function saying I will work with a user value. However, line 15 is our traditional polymorphic function in Go. What this function is saying is I will work with any concrete data that exhibits the full method set of behavior defined by stringer. In other words, it can string. You see, line 111 is we're asking for data based on what it is. And line 115 is asking for data based on what it can do. That's how we write polymorph functions today. It's based on what you can do. And then the compiler can validate that any concrete data you're trying to pass through can and does exhibit the full method set of behavior. Now, we have a behavioral constraint here, except that stringify isn't a traditional polymorphic function because it doesn't want to ask for data based on what it can do. It still wants to ask for data based on what it is. And so this gets interesting. We want to write a function asking for data based on what it is, but be able to also validate that it can do something. So how do we do that? Because if I try to build this function right now, forget about what's happening in main for a second, but if I try to build this right now, look at the compiler. What does it say? It says Bill. Whoa, slow down. Whoa, you're calling a method named string that's undefined. I don't know if that T is going to be able to do that or not. Slow down. So we have some syntax choices here because we have to tell the compiler that I want to accept a value based on what it is. And oh, by the way, it has to do this too. And so the idea right now is to leverage the interface, since it is already a mechanic, to be able to define a behavioral constraint. And so what we're going to do is say this. We're going to say that type T is the generic type to determine a compile time, and whatever type you use, it better be able to have data values that support this behavior. And now with that in place, the compiler says, okay, we're good. You've now defined the behavioral constraint I need, and I'll make sure that not just any value can be type T, but only those values that can exhibit the stringer interface. And now when you come into main, and I construct that slice of users and that slice of customers, and we pass it to these different functions, the compiler knows that user values have that string. It knows that customer values have the string. Pretty cool. I'm not gonna, we don't have enough time. I don't have to implement anything new. You kind of see it and you kind of get it. The draft document from a year ago talked about adding a new keyword called contract for this. But a lot of us had problems with that because it was so closely tied to the interface. It became a really difficult way of kind of teaching and explaining it. So I am, for one, happy that the idea of a contract went away and that we're leveraging the interface to define a behavioral constraint, not just for our polymorphic functions, but for our generic functions as well. Now, something more interesting is that there is another type of constraint that is not behavioral. So it doesn't affect our traditional polymorphic functions, but it does affect our generic functions. Because remember, what is the difference between our generic functions and our traditional polymorphic functions? Our traditional polymorphic functions are asking for data based on what they can do. These generic functions are still asking for data based on what it is. And there are times where there are certain operations that can only be applied to a certain class of types, like plus, minus, bit operations, things like that. And so we need another way of defining constraints that aren't necessarily tied to method sets, but tied to behaviors around operators. And this is the last thing that I want to share with you. Now, let's start here on line 16. And I'm going to get rid of all of this for a second and try to just stay with me and not go, come back here, not go too far just yet, okay? Just look on line 16 for a second. That way you can see what I'm trying to do. I want to write a function named add that accepts a value of some type T and a second value of some type T, adds those two values of type T together, and returns a third value of type T. Great. So what do we know already? Well, we know we need this syntax because T is a generic type to determine compile time. But we also know that we need a constraint because you can't do this with all types. You're not able to do this if T is a user. We don't have the concepts of operator overloading in Go. That's not coming anytime soon. You can't do this even if it's a slice. You can do it with an int. You can do it with a string. Can't do that with a string. Can do that with a string. Interesting, right? And so we need a way, we need a syntax to be able to define a constraint that tells the compiler that T can only be of a certain class of types that support these operations. In the current draft, the idea is this: to leverage the interface once again, and to add a list of types that will constrain T. And ideally, these types should be able to support the operations that we're applying here. So in this case, what I'm going to say is type T is a generic type and it's constrained to the interface add only, which right now is this list of types. So if I were to try to pass a float 32 for type T, compiler would say no. I can pass any of these types, however. And this also works with underlying types. So if I do this, I do not have to pass Bill because Bill's underlying type is a string. It conforms, it complies. So for those types using underlying types will match that type list on line 15. Once again, that list has to be a list that would be supported by the operations. If I did this, we'd have a problem because you can't subtract toString. Now, I'm going to tell you a couple things here. This is an area of the draft that the language team isn't 100% happy with. And the reason is because once you do this, you can't use the interface anymore in a traditional polymorphic function. It makes no sense. This is a function asking for data based on what it can do, not based on what it is. And so you suddenly have a situation in the language where you can define an interface that just can't be used everywhere. It can only be used for these generic functions. So they're not really happy with that. And they're looking for some different ideas and thoughts. Now, if you've been looking at the mailing list, and I think these ideas have been shot down, but some of the ideas I've seen is to do things like this. Instead of defining an interface with a set of types, maybe you define the operators that you want to support. The other idea also is maybe to put the type list here instead. And then there's the idea of some pre-declared type constraints that might be able to solve these problems as well. But right now, this is what the draft is currently implemented to solve this type of constraint. And again, they're looking for interesting ideas and thoughts, and I've shared a couple of that I've read over the last couple of weeks. Okay, a couple more things here. I did talk to you about pre-declared type constraints. And one of them that they have implemented is called comparable, that would allow you to support this type of operation around these values of type T, right? This is a case where T could be a user, could be a customer. You can't compare slices, but we can compare user values or addresses and things like that. So this idea of a set of pre-declared type constraints gets interesting. That might even maybe be a package in the standard library for all we know right now. That's something that's interesting. Now, the last thing I want to share with you, and I'm at my 1:20 mark, so I apologize. Give me 5 more minutes here. There's just a couple of interesting things here. Let's get back. I'm going to break this down a little bit first. Let's go back to this match. Let's say I wanted to write this function called match that can accept a slice of some type T and a value of type T. What are we doing? We're ranging over the slice, and then for every value in the collection of type T, I want to call this method called match, accepting that value of type T as a parameter. So what have we learned, at least in the last hour? Well, we know we have to define T like this because it's going to be a generic type. We also know that T needs to have this match behavior, so we need an interface that, in this case, I call matcher, to be able to define the behavioral constraint for line 76. But this method is different than the other one I showed you, because this method has to accept a value of type T. We don't know what the parameter is going to be. So look on line 70. Look at what I do here. We define the matcher interface, saying that the match behavior will accept a value of type T. And then we add our generic syntax there. And now everything kind of flows in. And so we can define interfaces with method sets that take generic types. There it is. And we see it being applied. Now, what you saw me remove before I did any of this was line 71. Now, I'm showing you line 71 because I want you to see, at least in the current draft, that you can define an interface that not only has a behavioral constraint, but a type constraint as well. Now, in this particular case, let's be honest, I don't need the type constraint on line 71 because this function's only using behavior. It's not like, and it wouldn't necessarily make sense to do this, but it's not like I'm doing this, right? So there's that. And I have struggled to find a practical example where we need to mix these two things together inside of an interface. Now, we might determine that this is really not necessary, which could potentially solve this problem here, and maybe we can do something differently. However, in one of the meetups during the discussion, an interesting thought had developed. I found it super fascinating. They told me that they were working on a product that had high levels of regulatory, that required high levels of regulatory checking. And they ran into a problem where they had this function that had to be restricted to the different types of data they would run through it to make sure that they were compliant. And then somebody didn't hack some code and then ran some like empty methods through it and got things to work. And the thought was, you know, this could help create a constraint on functions where we don't want any developer to define any sort of type with, say, match behavior and then run it through. Where this is kind of adding almost a regulatory check to say in the code, I don't care about every value that can match. These are the only ones that I will allow to run through this function. So it's kind of an interesting idea when you think about maybe applying some regulatory feature functionality in code base to restrict functions to very specific types. I don't know. It's an interesting thought. But if it's deemed that this isn't really necessary, then maybe this isn't going to be necessary. And maybe you end up with something new to apply this. I don't know. The other thing you should be aware of, though, is you cannot do this. You can't define two interfaces for a T. It's only one constraint. So you would have to be leveraging some form of composition to do that. The only other thing I want to say is if you add a second type and one type has a constraint, they all need constraints. And this is why if you start looking at code, you might see the use of an empty interface as a constraint in a type list, because once one type has it, they all need it. You don't really need a constraint here, so use the empty interface, all right? So if you ever see that syntax, you're understanding what it is. Okay, it is 8:26. I went over about 6 minutes. I apologize for that. But with that being said, I have really gone through in the last, say, hour and 10 minutes, the big bulk of the syntax in the draft. The other examples give you a little bit more practicality and a couple of more complex concepts that are in there. But this is the basic syntax and what we're looking at for a first release. And a lot of it is the reduction of the empty interface and the reflect package, where the code we're writing could just be more readable and comprehensible using language syntax. I don't want you to think that that means that I think the reflect package is bad. I love the reflect package. I think when it comes to marshalling and unmarshalling and decoding and data validation, you would rather do that with the reflect package than try to do that in a generic way. So this isn't about the elimination of type assertions and reflection, but I think it does lend itself to reduce that in code bases when it's kind of getting in the way of usability and readability. I also think this first release is going to be great in places where we could potentially now have a package in the standard library for some concurrency patterns and channel patterns. And I've played with that a little bit in the repo, so you'll see a channels there. And I kind of experimented with what that could potentially look like and how that could work. And so you can see that there. I think having a context maybe that isn't necessarily an empty interface value bag could be interesting. I don't know, because everybody can add to the context. So maybe not. And then obviously our container types and sorting and things of that nature. So I think you'll see some enhancements to the standard library, some new packages, and I think we can reduce some of the complexity. I have other opinions, but you've heard from me long enough. So what I would like to do, I've gotten rid of my screen sharing. Good, everybody can see me. What I'm gonna do is switch into this mode where I can see everybody. There's still 12 of us, so that's fantastic. What I'm going to do is walk through. I'm going to start with Daniel. Daniel, I'm going to ask if you have any questions first, and then I'd love to hear your thoughts. Some things I'm interested in hearing is from everybody is what do you think about the syntax? Does it feel like Go? Does it not feel like Go? Any things that you like, don't like, concerns, fears? But take about 2 minutes each, just to respect everybody's time. So we'll start with Daniel.
Yeah, that's a little loud. Sorry. Can everyone hear me okay? A little better?
Yeah, we're good.
Okay. So I think the most confusing thing to me was looking at line 59 of underlying type.
Let me bring that up.
So in there, you were using a type that has an underlying type, and you use the type variable t on line 59. It wasn't clear to me. That seems to be kind of undefined there. When you're using that as a receiver, does it just mean that there's whatever's in those brackets next to that ends up being defined as a variable for the purposes of line 59?
Yeah, I have an experiment. You know what? Let's do something here. I have an experiment with this, but my thought right now is that this type T is being bound to the method set. So I do not think you can use, and by the way, these names can be anything you want, right? They can be long, short. We have to create standards around that as well. But I don't think this will compile because this method is bound to this type list.
I see.
Right?
Okay, so if you wanted to use, say, 2 vectors and everyone was using type T as their type variable, then would you have a conflict, or does that only happen for the receiver and not for the...
Actually, it worked. It worked. So the compiler translated all of this. Now, that's interesting because I didn't think it would work.
So then what happens if, say, you put in vector bracket int 8?
Oh, no, you can't hard code anything here.
See, that's you see what I'm getting at? Like, it seems a little odd that then that gets immediately, that becomes a type variable there when, you know what I mean? Well, that's one thing I thought was a little confusing.
All right. Yeah, but again, you're trying to say that this method should work with this vector for any type T, right? So you wouldn't want to hard code that here. You would hard code your int here.
Oh, I understand that it doesn't necessarily make sense there. I just from
like the syntax.
Yeah, the syntax felt a little odd to me. I'm used to in other languages with generics, I usually will see them define for each time that they're using it. They'll say, okay, we are defining a type variable here that we're going to reuse throughout the syntax of this declaration.
So you're saying that they should have done this?
Yeah, that seems like that would make more sense to me. But
I think it's nice that they can build the methods around that, and you don't have to add any more. They're looking for ways to reduce, right? Like,
realistically, I'll get used to any syntax that we come up with, right? And if it's specifically for receivers, then I think it's fine, makes sense. But if it didn't apply for that, if it applied, say, for method, for function parameters, right now there's various different variables, right? And I'm not sure it quite works the same way. That's what I'm trying to square.
And remember, we're dealing with a tooling implementation, not a compiler implementation.
Mm-hmm.
So, but I do find it interesting that this worked because I'm going to talk to the language team about that.
Yeah.
I guess
if it didn't work that way, I imagine that you'd have some pretty interesting issues where you might have a function parameter where something that uses type T in its underlying type definition.
Yeah, so I have some example code where I actually use longer names when I know something's specific to a return. So I might do something like this on a function. So I don't know, but my brain, it's the first time I'm experimenting with this, but my brain hurts because I want to see, this is probably going to be linting shit. Oh, sorry, linting stuff,
Yeah.
right? Where linters are going to say, what are you doing? Just, you define T here, use it everywhere, right?
Yeah.
Anyway,
When
yeah, that's good stuff.
speaking of longer names, by the way, you had said that if somebody were to restrict someone to using pointer semantics, you'd end up with some odd kind of behaviors. Like it might look a little odd, or you end up with some unexpected errors. Say, at that point, do you think it would be good to use a longer variable name, say T pointer instead of T? Or in your experience, does that seem to be overly verbose and inflate things?
What I'm seeing out of the design document, and I'm not going to explain this code, but I'm seeing this syntax for pointer T.
Yep. Okay.
All
Yeah.
right.
Cool.
And this is a really complex example of needing a pointer type T, but needing to bring T in first. So I'm not going to go through it, but this is what I'm seeing right now in the draft, PT.
Okay.
When it's going to be explicitly a pointer. But one of the things I've told I hate when I say the word told, because who the hell am I? One of the things that I've asked the language team is that when a final version of this is all set and ready, that the language team spend a lot of time documenting best practices, idioms, and a lot of examples that we all can leverage in terms of teaching, because we're all teachers at the end of the day. We're teaching at work. We're going to be using it. And they've agreed and they've said, yes, we're going to have all that. And I hope to be a part of that a year from now and really make sure there's consistency there. And then those will be our guidelines and stuff for these types of questions.
Well, I will cede my time for now. I do have some other questions, but I think there's other people in the room that do as well, and they probably have some of the same ones as me. So.
All right, we'll come back then when we're done. Franco.
Sorry about that. I'm trying to look for the unmute button. Yeah, just just in terms of like thoughts on it, I haven't been following too much of the generics discussion. I'm curious, does that also include any talks of like operator overloading? Instead of having to use multiple and subtract and add functions.
There's going to be no operator overloading in this. I will, if they ever do it, I better be retired. And then it's operator overloading, constructors, destructors, these types of things, they hide the cost of code. Go is very much against hiding the cost of code. It's just not, it's not going to happen. It's not even, somebody brought it up, and I think even Ian pretty quickly said, yeah. Ian's very diplomatic, and I think he just said, yeah, we're not thinking about that right now. And I read it as, yeah, no, that ain't going to happen.
Yeah. I kind of figured, I mean, generics itself was such a contentious issue to begin with. So I was just kind of wondering, where there were those discussions going. This is probably the first time I've ever got any kind of like bearing at what's currently going on with generics. So that's, I guess, one question I had. I kind of had, like the same, thoughts that Daniel had. I think one thing that I also, was, that seemed a little odd to me was that kind of like changing the way interfaces work, and that, you're kind of having to specify a type. So I hope, like, as you mentioned before, like interfaces are what kind of define what can be done. And I kind of hope it doesn't get muddled up. So that's.
They don't either. I've talked to them directly on that one.
Yeah.
They're not 100% happy with it. At the same time, it might be the best option for the language, and it potentially gets in. But this is why I'm having these meetups, because there are a lot of people talking in the regular channels, but that's not everybody.
Yeah.
And so you might come up with some brilliant idea, right? And it just has to be heard.
Yeah. Well, I don't know if anyone else has anything else to add or say. So
So
I'll
who's
also.
next on my list? Bern. I'm going to try. Biren.
Birinder, the way my wife says is beer ender, Birinder.
Horrendous.
Like, and you got Ender's Game, beer and friends, so Birinder.
Nice. So do you have any questions and or
Uh,
thoughts?
Nope. I'm just like I said. I mean, I'm just a couple of weeks into the language, so I'm glad the code that you used was at least beginner friendly in a way that I could kind of follow along most of it. So that I think was really good. I mean, I was able to kind of follow along most of it, and apart from that, since I've not used Go that much, that I can kind of give any valid or rather good comments in terms of this is good or that is bad. So I'm still kind of just learning, but yeah. Overall, I think it was fun. I mean, I kind of enjoyed.
Your question then. You're a software developer, so what language are you most familiar with, and did you use generics in that language if they had it?
Java.
Did you use generics in that language?
Yeah, I mean, so I mean, compared to that, I don't know. I mean,
it's a curious question sometimes for me because there aren't a lot of C# developers that move to Go, but there's a lot of Java developers. And
I mean, honestly, I had started my career in C, and then going back and kind of learning, starting to learn Go. I'm actually finding it really, really interesting. I was talking to someone else the other day. I'm like, I'd now want to find a job where I can actually do code during my daytime and not just play in the side. Because it seems like a really fun language. I'm enjoying it so far.
Nice. All right, let me move over to Chris Means. Do you have any questions and or thoughts?
No questions. It all makes sense. I was previously a C# developer many moons ago. I've been doing Go for maybe the last 6 months, more in my spare time than work time, but mixing it up a little bit. I guess my only comment is I do find the extra, using the square brackets to be a little confusing. Coming from .NET, C#, I'm used to seeing angle brackets there. That would seem more natural to me and not be confusing, where I think I'm looking at an array.
So since you bring it up, and I don't talk about it unless somebody brings it up. In Go, we cannot have the angle brackets. And it's because of backwards compatibility issues with the current language. So I kind of documented it here in the blog post. So a lot of people want this instead of the square brackets.
Yep.
The problem is this code works today in the language. See how we're declaring 4 variables with comma delimited? And then you have the comma here. I can probably even bring this up in the playground. So you see how this works, where the compiler's going, okay, this is for A and this is for B?
Sure.
The problem is that if we use the angle brackets, right, that's the syntax. Is it what we had before, or now is that a generic function call? And there's no way for the compiler to figure it out. And the compiler in Go is really about performance. It's a compiler that has taken a lot of care to only have to do, and I'm not a compiler developer, but 2 passes to go through here, no look aheads. Compiler performance is critically important to the community, and to be able to figure this out would take compiler time. So that's why there are no angle brackets, or it's not even a choice. But at least the square brackets are not setting a precedent. I think the D programming language and one of the functional programming languages, I want to say Scala, but I don't know. use the square brackets. So at least we're not setting precedent there.
Got it.
Just a quick add, Bill. The same thing in Java. Java uses angular brackets as well.
Yeah.
Okay, well, I appreciate it. Thank you.
How about
I'll cede my time.
Justin's going to skip?
Yeah. Hi, guys. Sorry, first meeting. Great talk, Bill. Thanks very much. Just wondering, like a bigger picture plan. What's the plan with the standard library? When are people going to start rewriting the standard library? Are people thinking about that now? There's at least a transpiler, or are they waiting until everything's really nailed down?
Yeah, all we have is a transpiler, okay? They're really waiting for the syntax to be nailed down before they start any implementation detail. And then that starts the next big debate. Because one of the questions that somebody's going to ask me here, and I saw a little bit of is performance. Is this going to make Go run faster in cases where we're using the empty interface and reflection today? And unfortunately, the answer is we have zero clue, because they have to make a choice that has trade-offs. And just to give you an example, okay? They could choose to do exactly what the transpiler is doing. And for every generic function for a given type T, they could write the function out in that concrete type, right? Now, the nice thing about doing that is we'll probably get performance out of those functions, and you might even be able to eliminate some escape analysis here and there, right? Sounds great. What's the trade-off though? Larger binaries and longer compile time, because you got to build all that out and your binaries are bigger. And remember, compile time is important. So what's the opposite of that? The opposite is they could leverage the same generics that they're using today for the built-in functions, write a single generic function that could be used for all types T. Now, that's going to probably save on compiler time and binary size, because if you used 30 types, there's still only one function, but you won't necessarily get the performance boost you're looking for as if it was actually written out in that concrete type. So these are just two options that they have, right? There may even be more. Now, I know they haven't implemented anything yet, and I haven't heard them talking about it. And I'm afraid to even ask them, because they will probably turn around, Bill, we're not even there yet. But I'm sure they're having some discussions, all right? And then we got all of that has to come once the syntax is kind of in place and clean. I have no idea. I don't know. I hope that answers your question, or it gives you some even more insight on what has to be done next.
It does. Thank you.
All right, Chris. Next, Chris.
Yeah, no questions right now. We had an interesting discussion in the chat about the behavioral constraints example, and whether or not you could simply write a stringify that accepted a slice of stringer. But Justin and Matt set me straight. You'd have to go through the thing that you were trying to stringify and assert each one of them to stringer. So I don't know.
Oh yeah, with the empty interface, you always have the type. At the end of the day, you'll have to type assert to the other interface. Yep.
Right. Yeah.
Right.
That was not clear to me, but yeah. Otherwise, yeah, fantastic. I think I'm gonna have to spend a lot more time playing with the syntax to get it in my head.
Yeah, and that's one of the things I'm hoping that if you have some time, is look at your personal projects or work projects and look at areas where you're using the empty interface and reflection specifically, and see if there's opportunities to reduce some code complexity by applying it. Now, there is always fear that people are going to do with generics what happens with channels your first year in the language. And you can't necessarily stop that, but I'm hoping that the first 10 years of learning not to abuse channels will maybe cut that down to 2 on the generic side. Who knows? Yeah, so we'll see. But that's not a fear that should stop us from bringing it into the language. And, you know, I've been coding for 30 years. I code in C++, I code in C#. I never used generics because it made the code so complex, I just never wanted to deal with it. So I doubt I'll ever use it professionally, even when it's in Go, which then is like, Bill, why are you doing this? Why are you having this conversation? Primarily, I'd like to see Go be as big and strong and as popular as Java. And this can happen in the next 10 years. But for that to happen, the enterprise has to start using the language. And for the enterprise to use the language, they've told us over and over and over. When I say us, I don't work at Google or the Go team, but through the surveys and things, they've basically told the Go community, if we can't build our frameworks the way we do today, we can't use the language. And so it's an important feature whether you agree with it or not for the enterprise. And I'd like to see the language just grow more over the next 10 years. I think it's good for everybody. So if that means that we've got to add something like this to the language to bring in more people, and we all have to spend more time teaching and showing constraint, well, guess what? I think the trade-off's worth it. All right. I think Daniel said he may have had a couple other thoughts or questions, so I'd like to give him a chance to share that.
Yeah. One thing when you were talking about the add-only interface, the concept of using interfaces to form some kind of contract.
Yeah. Let me
it kind of reminded me a little bit of type unions and intersections in TypeScript. I'm not sure if you're familiar with the syntax of TypeScript.
I'm not. I mean, I only saw unions in C, right? When we're kind of bringing types together, but
I'm not. I don't think I've ever used that in C. I don't think I realized that it had it. In the case of TypeScript, so TypeScript is compile time only type checking. Right, it compiles down to JavaScript, and it doesn't, as it's transpiled, and so all that type information is actually lost at runtime. So I think in some ways similar to Go, if it implements the behaviors that you're looking for, it fits. If it quacks like a duck, it is a duck. That kind of behavior. That's exactly how TypeScript behaves. And the way that they have solved this is that you can define, for them, they make it so you can define a type as, say, a union of types. So they use the set operators of, just a pipe as like an or, right? Think like a binary or, or an ampersand as an intersection, or an and. So saying that something needs to have all of these fields or all of these behaviors implemented, or this can have any of these behaviors or types implemented, is kind of their, and I pasted a bit of an example of kind of what that would look like, what that looks like in TypeScript in the chat.
So here's something cool, and it's example number 7, where I think another area where the type list adds value is right here. And you see how I have an interface called entities for type user and customer?
Yep.
On line 88, I can now access the ID field from both these types. I don't have to do it through polymorphism. I don't have to write a setter. Now, this hasn't been implemented in the tooling, though the draft supports it. But I was experimenting here with, could I write a generic function where I didn't have to create an entity kind of based, an interface that's more based on something that's not reusable, right?
Yeah.
All because I want to access a field. So I kind of in line a little bit with what you just said. This is an interesting part of the draft for me, to be able to write generic functions that can access fields instead of me having to write an abstraction layer of behavior around that data access, right?
Yeah. So in the case of this, where you have type user customer, is that would be an or. It can be user or customer.
It's always an or, right?
And so then you could also say that this has an embedded field. You could just say, user customer. That would be an equivalent to more like an and. It will be both.
Yeah, well,
right?
yeah. As soon as I try to access ID, then the compiler needs to validate that all those types have an ID field, let's say.
Yeah.
And the compiler can do this work, even though this code won't build right now. It can do this work. So I find that exciting because I think what happens in too much code is people go interface crazy because they want to over abstract, or they're like, now I need a setter because I want to make this code a little bit more generic. And I'm like, just pulling my hair out.
Yeah.
And this kind of gets you away from that a little bit. So interesting stuff.
I think the reason I was calling out TypeScript, by the way, was specifically because they have some syntax that I've not seen, syntax choices that I've not seen before, that I really liked when I was using that language. If anyone else has used it.
I've seen it in Haskell. So.
Oh, you're right. Haskell does do that.
Yeah. And
although Haskell can infer tons of information about the types of everything.
Haskell's crazy land, though. I did that professionally for like 6 months.
Really?
Yeah.
That's cool. I mean, it's cool that somebody's using it professionally.
Yeah.
But yeah, so just a thought to maybe look at that syntax. I thought it was really cool, and I thought it functioned really well. I don't know how well it and how appropriately it would fit with the Go syntax because I'm not a particularly seasoned Go programmer. I've been working with the language for maybe 6 months professionally.
Yeah, I don't know enough either. Okay, so I've added those links again to the chat, and the survey is, for me, the most important one. I'd love for you to, if you don't have to do it now or today or tomorrow, or you can even wait if you want to play with the draft a little bit more. But I'd love for you to share your thoughts and ideas with the language team. And that's an opportunity to do it.
Oh, that's great. Thanks, Bill. And yeah, I mean, I think I have looked at that server before and maybe filled it already, but I will do that again. And yeah, thanks for doing it. Thanks everybody for joining. It was really good. Yeah, learned a bunch of things. I mean, I like how the syntax is going. I'm just like still on the fence about like some of the constraint and comparable and all those things, like how they are finally going to be, because that's where the complexity is going to come. So one of the examples that you were mentioning, Bill, were like you have one constraint, so you're like, put one type of interface that you define. Then you also need another one, and you end up like using nil interface. So that one is very interesting. Like, oh, we wanted to go away from nil interface, but it's still going to be there and present. Where like, oh, I don't know what this is going to be, so I will just use nil interface here. So that part is like, I'm looking forward like how that end up eventually.
Yeah, it will be interesting to see where that ends up landing. I don't have any unique thoughts or ideas, but I try to every day, but I didn't the last 2 days, is look at the mailing list every day and just kind of see what people are talking about and sharing. And I shared with you the ideas that I'm seeing that I thought were interesting.
Yeah, thanks a lot. Thanks for your time.
All right, awesome. Well, thank you for having me. It was nice seeing everybody.
Thank you, Will.
Thanks.
Stay safe and keep your meetup going every month.
Yes, that's the plan now. Thank you.
All right,
Yeah, thank you very much, Bill.
Yep,
All right,
thank
and
you, Bill.
I'll send me an email and I'll see if I have a link for the second recording somewhere.
Okay, I'll do that.